Hey guys, let's figure out what values make this function differentiable. Now, I hope you know by now that differentiable means that the derivative exists. And the easiest way to check and see for which values the derivative exists is to find the formula for the derivative and check its domain. So we will start out by getting a formula for this derivative. It is a cube root of 1 plus a tangent. We are going to need the chain rule for this. There is an outside function, that's the cube root, and there's an inside function, that's 1 plus tangent. So remember that the chain rule does derivative of the outside times the derivative of the inside. So the derivative of the outside is going to be, if we think of this as being this to the 1/3 power, now we can apply the power rule to that. So that will be 1/3 times 1 plus tangent of t, and now minus 1 from 1/3 is negative 2/3. But this is only the derivative of the the derivative of the outside. Now we need to multiply by the derivative of the inside, which I'm going to put in a different color because I can. Derivative of the inside is the derivative of 1 plus tangent of t. The derivative of 1 is 0. And so it just comes down to the derivative of tangent of t. That means we're looking at something like this. Secant squared of t, because secant squared is the derivative of tangent. Cleaning this up a bit, writing things on the proper tops and bottoms, it's going to look like this. 1 on the top, that's all, and then 3 times cosine squared t. Cosine? What do you mean? Well, secant is 1 over cosine. So this takes the 1 over cosine squared and turns it into cosine squared on the bottom. Makes sense, right? Then this is multiplied by 1 plus tangent of t to the 2/3 power. So for what values of x is the function differentiable? It's differentiable whenever the bottom is not equal to 0. So if cosine squared t equals 0, then this is not differentiable. Likewise, if 1 plus tangent of t equals 0, then it's not differentiable. So let's turn these into conditions on t itself. Cosine squared of t will be 0 whenever cosine is 0. So cosine is 0. Think about your unit circle. Cosine is 0 at the points where the x-coordinate is 0, there and there. So this is going to be not differentiable at points where, let's see, t is equal to pi over 2 plus n pi, where n is an integer. I won't use that fancy symbol for it. I'll just say n is an integer. Pi over 2 means that you land here on top of the unit circle, and the plus n pi part means that you go either forward or backward by some integer multiple of pi, meaning that you land either on the south pole of the circle or on the north pole again. So now let's look at the second condition. 1 plus tangent of t equal to 0. This means that you either have to be at a point where tangent is, well, not either or. You have to be at a point where tangent is equal to -1. That happens halfway through the second quadrant, and it also happens halfway through the fourth quadrant. So this is 3 pi over 4. And the same way that these solutions were separated by a half circle, these are also separated by a half circle. They're exactly halfway across the circle from each other. So this is going to be t equals 3 pi over 4 plus n pi, where n is an integer. So now we need to go and check the original domain of the function, because we don't want to claim that the function is differentiable at points where it doesn't exist in the first place. This is pretty easy to check, though, because the cube root of any function is going to, the cube root of any number, I should say, is going to exist. So the fact that this, I'll take away the scary looking 1/3 power there, the cube root of this function, it's going to exist no matter what. The only time that the function will fail to exist is if tangent of t itself is not defined. And we already took that into account because tangent is undefined at pi/2 and at 3π/2. But we already said that those are points where the derivative doesn't exist because those are covered by this condition. So for what values of x is the function differentiable? Well, it's easier to state the points where it's not differentiable. So it's not differentiable at these values, and it is differentiable at all other values. Okay, let's move on to one more. Differentiate the function. This is a stacked chain rule problem. We've got not even just an outside and an inside, but like an outside, a middle, and a very innermost inside. So here's what we're going to do here. We've got to do like, let's say u of v of w of x. Now, how do we take a derivative of that? Let's interpret it as a single outside and a single inside, as in u will be the single outside and v of w of x will be the single inside. I know it's a little dishonest, but hang on, it's going to work. When we differentiate this, it'll be u prime of v of w of x. This is the outside. But then it's times the derivative of the inside. And the derivative of the inside will be the derivative of v of w of x. Now, this we're calling the derivative of the inside for now, but in fact, it will be another application of the chain rule, except now we don't have too many layers. Now we have the normal number of layers that we're accustomed to, which is 2. So this will be, by which I mean just this part, it's going to be equal to v prime of w of x times w prime of x. And now this becomes doable. In fact, it's easy. So y prime is going to be cosine of, let me get a little bit of room around there. It's going to be cosine, by which I mean that I'm differentiating this one. It's going to be cosine of sine of x, where these things right here come from here. But now I need to multiply by the derivative of the inside of that. Okay, so the derivative of the inside of that is cosine of sine of x times, well, now this, at this point, I've gotten to the v prime of w of x. So now cosine of sine of x, that means I'm treating this as its own inside-outside pair. So cosine of sine of x, and then times cosine of x, that's the innermost inside. So here we have the derivative of the very outside times the derivative of the middle, and then times the derivative of the innermost inside. So this is like u prime of v of w, and this is v prime of w, and that's times w prime. So this entire thing right here, that's the derivative of this function. Cool, huh? Let's do one more. Find the first and second derivatives. This is not a typo. It is meant to be what's called a power tower. That's a real thing. Well, it's kind of a nickname. But again, this is going to be like a layered chain rule problem. We're going to take the derivative of the outside, which is going to be e to the x. And for this, I'm interpreting that e right there. That's going to be the outside function. Okay, if that's the outside function, I need to multiply by the derivative of the inside, which is there. And that is times e to the x. These are on the same line. This is not stuck up here in the exponent. Nope, it's not. That is on the same line as there. So now I've multiplied by the by the derivative of that. I guess I started this off by saying it's another like stacked chain rule problem with multiple layers. It's actually really not, because here we've got the derivative of the outside, but then because the inside is itself a function, you multiply by its derivative. But then there's no more layers. There's nothing inside the inside. And so we're already done. This right here is the derivative all by itself. And so we're done, which is kind of nice because that was the goal.